So yeah, we continue with the second parts of the reviews. We started with the introductions of FEA. Then last week we also see that when we formulate, either we use direct formulations or energy methods. I mean, a lot of time especially we formulate the solid mechanics problem, right? So a lot of time we are later on in elements. Okay, we put everything in elements, then we assemble the elements, so it will be in the matrix form. So there is a need to basically review back the matrix algebra, okay, before we proceed further. Okay, so just a recap of matrix algebra today. Then also more towards the ANSYS workbench, of the introduction of ANSYS workbench. Then yeah, you probably are getting better understanding or know more about this particular FEA software, as well as how to use it to solve, especially the solution parts. Either you are using the manual ways, okay, so how it's being solved in terms of metrics. Okay, so probably we'll look into this, and probably you will have a better idea, a recap back, what are the available methods to be used, okay, to solve if I have built the matrix out. Right, so matrix algebra. So just recap back some of the definitions of matrix. We have column matrix when we have column by columns. So here is A. We can say A is a column matrix, okay, in one columns. Row matrix. So C, we can say that it's a row matrix in one row. Then we will have diagonal matrix. Okay, so here we are referring to just diagonal matrix at here, right? Then we have unit matrix, okay, unity. So okay, so also in diagonal, but then or replace your diagonal matrix or replace that by 1. We have band matrix, okay, so from the diagonal, then you band, you have probably here you have the 2 1 and 1 2 bands, okay, at here, okay, so all around here. Then you can also increase to here. So that is from a diagonal matrix as a central. Then yeah, depends on how wide is your band matrix. Upper triangular, okay, so upper triangular matrix is from diagonal onwards. Then you have this, all the upper so-called this triangular, you have values lah. So that is upper triangular matrix. Lower triangular matrix, the opposites lah, from the diagonal against, then the lower parts of the matrix will have values, right? So you have L11, L21, L31, L41, then yeah, L22, 32, 42 until N2 lah, right? Right. So that are several several matrix definition that we later on probably we will refer back. So okay. So in terms of addition and also subtractions of matrix, right? So what we do is just the same matrix. Okay. If you have to ensure first they are in the sorry, anyone? They are. Someone is turning on their mic, is it? All right, sorry. Okay, so if you have additions or subtractions, then probably the same size of the matrix you can add. So from the A11 plus or minus B11, A12, B12, 21, B1, A21, B21, A22, B22. So just add them up, right, accordingly. at the same size of matrix. So multiplications, okay, if it's a constant, then beta here. So basically multiply all your matrix, okay, with the numbers with the betas. Okay, so if in the case of multiplication of two matrices, then you have to fulfill the rules. Okay, so you have the m times n matrix. Okay, so which is, let's say your A is m times n matrix, then probably B have to start with the n okay, n times B matrix. So you end up, okay, m times n times B, then end up m times B, the size of the matrix. All right, so that is thing that probably you have to take notes. So the size of the matrix have to fulfill that rules in terms of multiplications, right? So how you do it, okay, if you have a n times n matrix multiplied with n times n matrix, right? So you will have n times n matrix, okay, in multiplication. So what we do is the C11 here, A times B equals to C, okay, so C11 here, basically you have A1 multiplied with B11, A12 plus, okay, A12 multiplied with B21, then here plus the summation of all this, right? So that gives you the C11. So if you want C12, then you go towards the first row, second columns, then you have the A11 multiplied with B12, right? Then you have A12 multiplied with B22, then summation of all this, the whole, the first row and the second column of matrix B, then it will give you a C12. Okay, so that is what you see at here. So if you can also do partitioning or partitions, okay, 3 times 3 matrix. Let's say A is a 5 times 5 matrix, then you have here, if you have partition it in towards A11, which is these groups. Okay, then you have this is another groups, which is represented by A21, capital A21. This is another groups. This is another group. So that is the partitions lah. So if you have that doing the partitions of matrix, then probably the size of if you are doing addition and subtraction also have to be similar lah. Have to be same. So, okay, then you can add them up. A11 plus B11 basically is similar like what you see lah. Okay, this A11 plus B11. You have this A11 plus B11, A12 plus B12, A13 plus B13. Okay, so that is give you A21 plus B21, A22 plus B22. Okay, so it's this plus this lah. A23 plus B23. So that is giving you partitions. Okay, when you have what we call additions or subtraction in this case. All right. So in the case of you are doing partition, but then you're undergoing probably what we call multiplications, then you have this again the rules have to be follows. Also you have a 2 times 3 matrix, 2 times 3, 3 times 3, 3 times 3. Okay, then you want to multiply with C. C is 3 times 2, right? Then this is 3 times 1. This is 3 times 2. This is 3 times 1. So in the case of A multiplied with C, then you are looking into your A11. Okay, this A11 is, we know that M1 is 2 times C11 is 3 times 2, then you end up giving you your so-called the D here is 2 times 2 matrix, right? So in the case of 2 times 3, which is your A12 2 times 3, then you have C12 is 3 times 1. Then here your D21 is 2 times 1 matrix. Okay. Then D21, okay, D21 is basically your 3 times 3 matrix times 3 times 2 matrix. So again, you end up 3 times 2 matrix. So D22, you have here 3 times 3, again times 3 times 1, then you have a 3 times 1 matrix. Right. So in terms of partition wise, then you also can be done in that case. Transpose of matrix. Okay, so transpose basically, yeah, you transpose, so all your columns matrix basically become a row. Okay, so that is your transpose. So if transpose B and transpose again, then it will back to the matrix B lah. This one also the same. If you have A plus B plus C until plus N matrix, transpose it, then when you expand it, it's actually the transpose of A plus transpose of B plus transpose of C plus until plus transpose of N. So if you have a multiplication of matrix A, B, A, multiply with B, multiply with C, multiply with N, transpose of them, then you can rearrange it equals to, expand it into equals to N transpose, multiply with C transpose, multiply with B transpose, multiply with A transpose. Okay, the inverse one. Right. So if you have a symmetric matrix, okay, when I say symmetric, you can see that this is, let's say, our A11, A21, A31, A41, this 1 2 2 2 3 2 4 2, A13, A14, A23, A24, A33, A43, A34, A44. So you can see that from here, all right. So from here, the diagonal, okay, you have the diagonal matrix from here, A11, A22, A33, A44. Then you will see that the 2 1 1 2 giving the same value, okay, 3 1 1 3 also the same, 4 1 1 4 the same value, then 3 2 2 3 the same, 4 2 2 4 the same, 4 3 3 4 the same, right? So that is what we call symmetric matrix. So if you symmetric, then the transpose of that symmetric matrix is similar, okay, it's similar to that matrix itself. Okay, so whenever it is transposed or not, it will give you the same result. Okay, that is transpose. Then we need to know determinant, because if you still remember last week, when we formulate our problems a lot of times, okay, you have this the stiffness matrix K multiplied with U equals to the load matrix, the displacement matrix equals to the load matrix. Then if you want to find the displacement matrix, then we have the inverse, okay, of, then we have this. So a lot of time we need to find the inverse if you want to solve a problems, okay, I mean, using finite element methods. Then we want to solve a problem, then yeah, we need the inverse matrix. So to know the inverse matrix, then probably if you want to do manually, then probably you need to know the determinants. Determinant of the matrix here is you can do, of course, direct expansions, okay, like what we have seen here. So if I have a A11, A12, A21, A22, then you direct expansion, basically all here is plus, all here is minus. So it's A11, A22 minus A12, A21, right? So if you have a 3 times matrix, then probably again the same. This is plus all this multiplied C11 multiplied C22 multiplied C23 plus C12, C23, C31 plus, then all this minus. So you end up giving you this. Else, you can use what we used to learn before using the minor. So if you find C11, the first determinant for three-dimensional matrix, you have C11, then you take, you take this, okay? You take this part, right? So in the case of you have C, then you have minus. Here you have to put minus C12, okay? C12 is here, then you have probably here is C21, C23, C31, right? So again, C11 multiplied with C23, C33 minus C23 minus C32. Okay, so that is what you see, what you have learned previously. So in the case of the third one, okay, then you go back to plus C13. Right, so this is the matrix C21, C31, C22, C32. So again, multiply it, then you will get the similar results. Okay, so end up you have a C11, C22 multiplied with C33 minus C23, C32. Okay, minus C12. Here you have a C21, C33 minus C23. C31 plus, okay, C13. Here you have C21, C32 minus C22, C31. Okay, so let's just recap back. So end up you will have a similar like what you have seen here. All right, so that you give you the determinants. So how if we have probably, for examples, we have a 4 times 4 matrix. Let me show you, okay, a quick one. So just an example how if I have a 4 times 4 matrix, A equals to A equals to 1, 3, negative 1, 0, 0, 4, 5, 1. Let's say 2, 0, 2, 1, negative 3, 1, negative 2, 3. All right, so that is our A matrix. Then to find the determinants, of course, you can use the direct expansion methods. Okay, it's quite straightforward. Else, if you can take this equals to taking here the 1, then we have these particular parts. Okay, so we have a 4, 0, 1, 5, 2, negative 2, 1, 1, 3. All right, then we have minus 0, then the matrix is 3, negative 1, 0, 0, 2, 1, 1, negative 2, 3. Right, then we have plus 2. Here we have 3, negative 1, 0, 4, 5, 1, 1, negative 2, 3. Then we have minus back negative 3. We have 3, negative 1, 0, 4, 5, 1, 0, 2, 1. Right, then we expand it and all the right. So just to recap back this should be not so much issues for you. So we have equals to 1, right? Then we have again 4 times if you see this is 4 times you take 4 at here. Maybe I use another color so that you can see it. Right, so if I take 4, Okay, so we have these parts. So we have 4, 3 times 2, 6, plus 2. Okay, minus 2 is plus, minus 2 is plus 2. We have 4, 8. Okay, then minus, this is 0. Then we have plus 1. Okay, 1 here, we have to look into this thing. Here is 5. 5 minus 2 is 3. Right. All right, so that gives us the first part. Right, then we have this 0, then it's minus 0, then plus 2 again. Here we have 3. Again, we have from here we have 5 times 3, 15, minus 2 is 17. Right, then we have minus 4. Minus 4, we take these 2, okay, negative 3, minus 0. Right, so we have negative 3 here. Then plus 1, here is negative 1, minus 0. So we have negative 1. And lastly, we have plus 3. Here we have looking into this 3, okay, 3, 5 minus 2 is 3. Right, minus 4 again. Here we take this and this, negative 1 minus 0, so it's negative 1. Lastly, is this is 0, that is 0. All right, so you will give us 135 minus 0 plus 2, 51 plus 12 minus 1 plus 3, 13. Right, that give us the value of 198. Okay, our determinant is 198. So that is just an example. If you want to look for a determinant of a 4x4 matrix, yeah, that is what you can do. So if you can find determinant, probably we are one step nearer to determine the inverse of the matrix itself. So inverse of matrix is 1 over determinant. Then you find the cofactor of the A, then you transpose of that cofactor of the A, right? So that you see what you see at here. All right. Then if you this cofactor, transpose of the cofactor of A, then is what sometimes we call it adjoint of A. So 1 over determinant then of A multiplied by the adjoint of A, that gives us the inverse. All right. So if you have A, B, C, D matrix, then our adjoint here is referring to D, A, okay, this swap, sorry. So we swap between 2 times 2 matrix, in the case of 2 times 2 matrix, then this A and D is swap, then B and C, we put a negative. All right. Or if you have 3 times 3 matrix, then what you do is you find, of course, you can find the cofactor, then transpose it is basically our adjoint in this case. Right. So transpose again is like what you something similar like what you have done in the determinants. So transpose are cofactors. Okay, then you have this A looking for the first. Okay, let's say this is our cofactor C. So I'm talking about C11 itself. Let's say the cofactor of this matrix, the first C11 itself, we are taking this matrix. Okay, A22, A23, A32, A33. Positive, right? So for C, so-called 1, 2, C13, again the same. Okay, you have A from the A12 onwards, then you have A21, A31, A23, A33. But you put a minus here. So plus, minus, plus, minus, plus, minus. The second row is minus, plus, minus. The third row is plus, minus, plus back. Right? Then end up, you will have the cofactor, then you transpose that the entire cofactor, then it will give you the adjoint. Okay, so once if you have adjoint, then we have the determinants, then we can find the inverse of that matrix. So if I have two inverse of matrix multiplied with that matrix itself, So it's equals to the matrix multiplied the inverse of the matrix itself equals to the identity matrix. So like what we have dealing with, okay, a lot of time we want to find the displacement for a solid mechanic problem in using finite element methods. Okay, we formulate it using what we have seen that day, okay, last week. So we will end up with a stiffness matrix K multiplied with U equal to F, then U equals to K inverse F. So we have to find the inverse of the matrix in order for us to solve to find the unknown U matrix. All right, so solutions wise, okay, a lot of time our formulations, our finite element problems are using finite element methods to solve it. So we are in matrix form, so we are actually solving a set of algebraic equations, linear algebraic equations. So of course, if you have just 2 times 2 or 3 times 2, 3 times 3 matrix, the size, so probably direct methods, it's quite straightforward, okay? And talking about Gauss elimination method is the one that we used to use, okay, when we solve a set of linear algebraic equations. So we also here, if you're using matrix forms, then probably you can use this another method called lower triangular, upper triangular decomposition methods. So basically, what they do, what it does is basically you have the ax equal to b. Now we want to find x, right? Right. So instead of basically impute your A, okay, it decomposed into towards two matrix, okay, which is L, lower triangular matrix, and U, upper triangular matrix. So from there, it assumed that UX, okay, upper multiplied with X equal to Z, okay, lower multiplied with Z equal to B. Okay, so from there, if you can find the L, you can find the U. With the B, okay, you can find Z, right? With the Z, with the U, you can find X. That is something what it used. Later on, we'll look into this. Okay, so here, solution of linear equations methods under matrix. You will have using direct methods. Okay, here direct method you have Gauss eliminations, lower triangular or upper triangular. Uh, what we call LU decomposition methods here, or we have the iterative methods. So iterative method, basically they will find they will solve it iteration by iterations. So until the closest or the latest iterations, okay, the difference between these two below what we call the percentage below a tolerance that we set, okay, then we will stop. So basically we have to, the user have to define a stopping criteria for that programs or whatever the iterative methods to solve. Okay, so here it usually use the last two iterations, okay, of the solutions. So if it's not deviate too much, then it will stop, then it will give you the final solutions. So the two common methods here, we will have this Gauss-Seidel methods and also Jacobi methods. So the difference between these two is the Jacobi methods. Basically, if you have a set of values, okay, you want like what we have found. We have this. Let's say maybe I will just show you. I will go a little bit detail, but let you see what is it. So we have this. If you still remember, we have the K, then we have this F. If you still remember, right? So to find our U, right? To solve this, sorry, K inverse. So to solve this, or what we call, we have this K U equals to F, right? So a lot of time, basically, you have in terms of let's say you have the K1 U, let's say 1, okay, plus K, let's say K1 K2, okay, U2 plus K3 U3 equals to F1, right? Then we also have K1 plus multiply with U1 plus K2 multiply U2 plus K3 multiply U3 equals to F2. So basically we are having a set of linear equations, right? So the only difference for Jacobi, so you are solving the equations simultaneously, right? So you are getting the U1, the unknown of U1, U2, U3 in this case, right? Or here you are getting X1, X2, X3 in this case. Right. So Jacobi method here, it basically assuming, okay, a numbers, okay, a predefined numbers, okay, which is U1, U2, U3, it could be 1, 1, 1 first. So substitute into it, then solve it, the first iteration. So it will find after the first iteration, it will come up with another new U1, U2, U3, right? So this U1, U2, U3 after the first iteration will be used to solve for the second iterations. Okay, so you have at the end you have another U1, U2, U3, and then another set. So that is how Jacobi method works. But Gauss-Seidel method is a little bit different. Okay, so it will find, of course, it will give U1, U2, U3 as, let's say, 1, 1, 1 first. So the first iteration, it will find the U1. Okay, U1, U2, U3, right? But when it have determined the U1 will be used to calculate U2, okay, of the first iteration. And once you have the U2, the U1, U2 will be used to calculate the first iteration U3. So end up you have a U1, U2, U3 after first iteration, where the U1 is used to calculate the U1, it used the U1, U2, U3 of the first the 0 iterations. To calculate the U2, because the U1 have calculated, you have the U1 of the first iteration to be used. Okay, then you use the U2 of the first iteration, 0 iteration, and U3 of the third iteration. So what it means here is Gauss-Seidel method. It use it use whatever that have been calculated. Okay, so that is the only things. So if you have x, your x, you have x1 until x2, x3. If the x1 have calculated for that particular iteration, it will use. Okay, if you have x2 have calculated for that particular iteration, it will be used to calculate x3, something like this. Whereas for Jacobi method, all will be using the previous iterations values of x to solve for the next iterations. Okay, so that is the only difference. We'll look into more details. So if you want to solve a problem some sort like this, okay, you have 2 x1, x2, x3 equals to 13, 3 x2, x1 plus 2, x2 plus 4, x3, 32. So this, it can be actually similar to like what we have seen here in matrix format A, x equals to b, yeah? Right? So we have 2, 1, 1, 3, 2, 4, 5, negative 1, 3. This is our A. Then we have our x1, x2, x3 in matrix format equals to 13, 32, 17. So it's again similar with what we are formulating, right? Equals to F, like what we have formulated using our finite element methods. So we are solving a linear equation, algebraic equation, to get the x. So in this case, in our case, we are getting u. So it's very similar. So how we want to solve this? Of course, we can use matrix. In finding the inverse itself, inverse of A, then multiply with B, we get the x1, x2, x3. Straightforward. But in the case of you do not use matrix form, of course, you can use this Gauss elimination method that we have learned, I think, since our secondary. Okay, so we have 3 equations, 3 unknowns, then we can actually solve it simultaneously. So by using this Gauss elimination methods. So what we do is we look into the first 2 equations. So we have the equation 1, equation 2, equation 3. Then we basically multiply our equation 1 with 3 multiplied with 3 divided by 2, right? So that gives us the fourth equations. Then we also have our the second equations, right? So if I have second equation multiplied with fourth equations, then we will have these fifth equations between x2 and x3. Right. At the same time, we also can multiply our first equation with 5/2. Then we have the third equations. Right. We have the third equations. So the third equations multiplied minus our this one, let's say our sixth equations, equals to our sixth equations minus the sixth equation, then it gives us the seventh equations. Right. So from there, okay, we have here we have the fifth equation and seventh equations. Okay, this is our fifth equation, seven equations. Then we have our first equation divided by 2, right? Then we can actually solve our x2 and x3 using equation 5 and equation 7. So to find our equation 5 and equation 7 using this, okay, we multiply with so-called our 31.31 this is our equation 7. Then we multiply our equation 5 with 7s. Then it will give us this, let's say, 8. So at the end, minus it, we will get x3 equal to 72. 72 over 18, which is 4, right? So we have x3, substitute into any 5 or 4, 7, then we will get our x2 equals to 5. Then substitute x1, x2 equals to these equations, then we have our x1 equals to 2. So that is what we used to do it. Okay, if we manually, I mean, that is what we call Gauss elimination methods. All right. Next, beside Gauss elimination methods, we can use this LU decomposition method, lower triangular, upper triangular decomposition methods. Right. So again, we have this A x equals to b, right? Then what the LU method does was it split them, okay, this A matrix into words L and U, lower triangular and upper triangular matrix. So the upper triangular matrix, of course, you have the full upper triangular matrix, okay. The lower triangular matrix where the actually is the diagonal, okay, diagonal matrix is replaced by the unity matrix, okay, 1, 1, 1 at here, then followed by the lower parts, the lower triangular matrix. So it splitted this into words. Two matrix, okay. Your A now become what we call these two matrix. Then if you multiply them, if you multiply back them, then your A now become U1. Okay, this multiplied with let me show this multiply with this plus this plus this. Okay, then you have the this multiply with this multiply with this plus this and plus this and plus this, right? So the multiplications, I don't want to confuse that thing so much. So you will end up to give you a matrix of this matrix, which is equals to L multiplied with your U matrix. Right, then we can actually build relationships, a general equations that actually give us this. So if you can see that if you are looking into the upper triangular matrix, right? So upper triangular matrix, we want to determine from the diagonal onwards, then the top parts of the matrix, right? So in this case, if you look into this, our top parts, okay, if you look into these particular general problems, okay, for j equals to k to n, Then we have probably, maybe I need another empty sheet to show you. All right. Then we have our general, okay, matrix. Okay, sorry. We have our general matrix. If you look into the matrix just now, equal to A, K, J minus K minus 1, summations, P equals to 1. Then we have the L, K, B, U, P, J. So it's actually looking from J equals to K to N, right? So just now, if you look into this, the upper, sorry. So we are determining, okay? We want to determine a general equation that can help us to determine this L minus U. And our upper UKJ, our so-called UKJ here, okay? We want to determine this will help us to find this. This will help us to find this lah. So we want to find, you see that our upper triangular matrix, you have U11, U22, U33, which is the diagonal matrix, all we need to find. Then the upper one, which is U12, U13. All right. So if you look into this, basically, if our upper, it is actually happen from a diagonal onwards lah, upper onwards. Right. So with our K equals to row, right? Our K equals to row, J equals to columns, right? So in this case, our J equals to column, right? So if you look into this, then we have our K equals to 1, J equals to 1, right? Then we also have, basically, you see that it starts from when I have K equals to 1, J equals to 1, then we are determining what we call U11, right? Then J equals to 1, K until N lah. I mean K to N, so you can U12, U13 until, right? Further. So if I have a K at the second row, number 2, actually J equals to 2, meaning I am taking U22. So if I have a matrix, U11, so we are taking U from the only the diagonal onwards, okay? Only this part, right? So you have U22, U23, U24, right? So you do not take any U21 in this case. So same with K equals to 3, J equals to 3. So you are taking U33 onwards. Okay. So if you are substitute into here, okay, let's say for example, I want to find my K equals to 1, J equals to 1. So if you look into this, so looking into this equation, we have U11, then we have the A11 minus, when I K equals to 1 minus 1 is 0, P equals to 1, L 1, P, right? Then U, let's say this is, this is from 0 lah, basically. So actually the whole parts here, maybe I will just erase it to not to confuse. Okay, so U11, if you look from the U11 itself, this K now is 0 minus 1, P equals to 1. So this thing is not valid anymore, so it becomes 0, right? So U11 is equivalent to A11. That is what you can get. Similarly, if you are looking for U12, okay, because your K, the first row the first row is K. Okay, so your first row is 1. So here, this particular part are all 0. The second parts of here is all 0. So it's equivalent to A12. A1, U13 is equal to A13. So what it means here, the first row of your upper triangular matrix is actually equal to your A. Okay, so this U1, U11, U12, U13 is actually equivalent to this. All right, so that is what it means lah. All right. So if I'm going for the second row, okay, which is U, of course, if I'm going for second row, it have to be U22 onwards lah. So if U22 onwards, then I have a A22 minus 2 minus 2 minus 1 from P equals to 1. Then I have my L. 2 minus 1 is 1. So it will need from 1. So we will have the L 2, 1, U 1, J is 2. Okay. So here again, you can find the U 2, 3 from here. U22 here is equivalent to what? Equivalent to here equal to A22 minus L21 U12. Okay, so from there you have to find, of course, the L21, which is this one. Okay, you need to determine this using the other formulas. Okay, then U12, of course, you have obtained here is equivalent to A12. So this you have to determine. Now you have to determine this. All right, so that is upper side or upper triangular matrix. So we have to solve this matrix. We have to build this matrix. I mean, from the equations, the decompositions. So for the lower matrix, lower triangular matrix, if you look into another one. So the lower triangular matrix, then probably if you see here, you have the equations is L, I, K. I is the row, K is the column equal to I. AIK minus K minus 1, P equals to 1, LIP UBK over UKK. Okay, so if you see that it is for I equals to K plus 1 to N. Again, if we want to say this, it is actually below diagonal. Below the diagonal matrix. So if you have a matrix at here, if you still remember that our L itself, the diagonal all 1, then followed by our L, right? So L. Okay, so that is what we have. So in the case of I have my sorry, what's wrong? I equals to row. Then I will have my L11, L12, L13. K equals to column. Right? So if you look into this, then if I have a K equals to 1, K equals to 1, my I itself, okay, it have to be plus 1, K plus 1. So it have to be 2. Okay, so meaning to that for the first column, this is the column, all right? This is row. But for the first column of matrix, I have to start from the second row. What it means here, you only determine our L 21 onwards, then L 31s, L 41s. Okay, so you are taking this. Okay, if you have the K equals to second column, then my I equals to 3. So we are taking L 3, 2 onwards. L 4, 2, L52. So again is here. So that is how it look like. So again, you substitute everything in, then probably you can find. So for example, I have an example. Yeah, again, let's say I have an example here again. Right, if I have an A matrix of 3 times 3 matrix, A equals to 2, 3, 5, 1, 2, negative 1, 1, 4, 3. Right. To find our L, we know that is 1, 1, 1. Then I have L21, L31, L32, 0, 0, 0 to be determined. My U matrix, my upper matrix will be U11, U12, U13, U22. This is 0, 0. Then you have U23, U33. Okay, so that is the things that we have to determine. So based on the equation, general equation that we have obtained just now, right? So first, if you want to find U, K equals to 1, J equals to 1, then I can find my U11 equals to A11 equals to 2, right? A11 equals to 2, right? Right, I mean, let me not to confuse you. This A11, this is A21, this is A31, A12, A22, A32, A13, A23, A33. Okay, so easily can be seen later on. Then we can find the second. Okay, second, based on upper, we can find the second column, J equals to 2. We have U12. Also, we know that it's U1, A12, so it's 1. Then we have also K equals to 1, J equals to 3. We have U13 equals to A13 equals to 1. So we have determined probably U11, U12, U13. Right? Then if you still remember, if you want U22 just now, right? If you want U22, we need L21. So probably we can start with we have to find L21, right? So to find L21, we use that formula. I mean, to find the L21, we have I equals to 2, K equals to 1, L21. So we have L21 equals to A21 minus 0 divided by U11. So end up is 3 over 2. Right. So we also can find the L31. Okay, I equals to 3, K equals to 1. We have L31, A31 minus 0 over U11 equals to 5 over 2. Okay, so basically we substitute into here these equations. So our A, if I want to find our L, let's say 31 here, right? So we have our I, our so-called I equals to 3, K equals to 1. So our L31 is A31 minus my K is 1 minus 1, P equals to 1. So the whole thing is also L3. Basically, the whole thing is 0 because this is 0, right? So that particular part is 0. So we have divide by U11. So it's actually A31 over U11 in this case. So that is what you have here, 5 over 2, right? Then from there, we can actually find our U22, which is my K equals to 2, j equals to 2. We have u22 equals to a22 minus 1, p equals to 1, l21, u12. So it equals to 2 minus l21, which is already obtained, 3 over 2, u12, which is 1, so we end up 1 over 2. Right? Then we can find also k equals to 2, j equals to 3, u23 equals to a23 minus 1 over summation p equal to 1, so we have l21, u13. Right? So again, we have the a23, which is a23 is 4 minus our L21 3 over 2, U13 here we have obtained is 1, right? So we have 5 over 2. So again here our U22 done, U23 done, right? Then our L21 done, L31 done, right? So now we are leaving only L32 and L33. So if you want to find L so-called I equals to 3, K equals to 2 to find our L32, then we have A32 minus P equals to 1. We have a L31 U12 over U22. Right? So it will give us minus 1 it will give us minus 1. A32 is here, okay, is minus 1 we have obtained. Then minus our L31 and U12 is negative 5 over 2, 5 over 2, U12 is 1. Then over U22 is 1 over 2. So it gives us negative 7. So at the end, we can find our K equals to 3, J equals to 3, U33. So we have A33 minus 3 minus 1 over P equals to 1, L3B, UB3. So it's actually equals to A33 minus, we have the L31U13 plus L32U23. All right, so it will give us 3 minus 5 over 2, 1 plus negative 7, 5 over 2. Okay, so it will give us 18. So end up our L, we will just write it here. Our L here is equivalent to 1, 3 over 2, 5 over 2, 0, 1, negative 7, 0, 0, 1. Okay, our U equals to 2, 0, 0, 1, 1 over 2, 0, 1, 5 over 2, 18. So we decompose it, okay, into lower and upper, okay, lower and upper triangular matrix. Then once we have decomposed it, right, then based on these particular forms, we can determine our, you see we have the L, we have the B, right? You see this L, Z equals to B. So if we want to find Z, then we need only B, and we only need the B, sorry, we only need the B matrix and also the L matrix, the lower triangular matrix that we have obtained. We can get our Z. Okay, here we have our Z1, Z2, Z3. Okay, so from here, if we have the Z, we have the upper, and we have the upper again, then we can find our X lah, in this case. So we can solve the X is this itself. Right. So that is how you solve it lah. So for example here, okay, a matrix of 2, 3, 5 that you've seen. Okay, you can decompose in towards the lower and upper matrix. Right. Then from there you can find your so-called x3, x2, and x1 based on you see the z. Okay, we have to find your z1, z2, and z3 lah, in this case. Okay, from this you find your z3, z2, z1, right? Then substitute into here to find your x3, x2, and x1. So end up you will get 4, 5, 2. Same with the Gauss elimination methods lah. All right. So that is a little bit longer. I mean, but then yeah, but it is the step by step is already fixed lah. So straightforward, but then a little bit longer lah. You may consider that. Right? The direct methods, then we have the iteration methods. Okay, iteration method, we have Jacobi. So if you look into the mathematical formulations that Jacobi, how Jacobi method works, basically you see that you have this, again, you have the A matrix from X equals to B, right? So if you rearrange everything in terms of X1, X2, X3, so you'll find out that our x1, okay, equals to, from here you can find x1 equals to your divide 1 over a11, then you have b1 minus a12 x2. Basically you rearrange everything like x1, x2, x3, right? Then how they find this x1, x2, x3, okay, you have to give x1, x2, x3, okay, predefine, okay, initial values, okay, and what is the initial value for it to start, so that what we call our x zero iterations, okay. So you substitute into all these equations your x2, x3 until xn, x1, x3 until xn. Okay, substitute everything with the initial values. Then you find your x1, x2, x3, your x for the first iteration. Okay, so these first iterations, okay, will be used for the second iteration. So you, from second iteration, you will use this new x1, x2, let's say x3 for the first iterations. In this is 0 iterations, right? Initial value is 0, then 1, then you will substitute into your second iterations, you get your x2 equation. So in general, you can see that all your x value of the previous iteration will be used to solve or to calculate your x in the next iteration, k. That is Jacobi. So in terms of matrix form, I mean, you can also solve it in matrix form. Ax equal to b. What it does was, if you look into, sorry, let me. So it will again decompose in towards your A. Your A matrix equals to D. Okay. Diagonal matrix. Okay. One is diagonal matrix. One is a lower triangular matrix without the diagonal parts, and upper diagonal matrix without the diagonal parts. Okay. D minus L minus U. Okay. So your A will become D minus L minus U. So if you, this A become D minus L minus U, rearrange everything, so okay, then you will have your X, okay, dx, okay, L plus U, putting out. So here L plus U, here we call it R lah, remainder lah. R equals to remainder, remainder. Right. So what it means here is all the matrix except the diagonals. All your matrix numbers with except the diagonals. So you here you have the diagonal and the remainder lah, basically. So here you have diagonal and remainder. So if you take the diagonal out, dx, then the remainder basically you put into the other side, L plus Ux. Okay. plus b, which is your previous iterations. This is your previous iterations. Then rearrange everything, you can get your x of the current iterations lah, k. Okay, so that is the formulas lah that you can use. So at the end, if I want to find my next iteration k plus 1, I only need the x value of my current iterations and diagonal matrix of your A, and also the remainder matrix of my A. Okay, so I need the inverse. I need two things. Inverse of my diagonal matrix. Of course, if you have a diagonal matrix, the inverse basically is the 1 over A11, 1 over A22, and 1 over AN. It's easy to determine. Okay, then multiply with our B matrix, then minus my remainder matrix with the x k with the current x. So my remainder, of course, is the L lower the triangular plus the upper triangular. Okay, these two parts add together. So if I have a matrix 2 times 2 matrix like this, okay, so using matrix form of a Jacobi methods, so probably you can find your what we call your diagonal is 2, 7, your remainder R is 0, 0, 1, 5 lah. Right? Then you have the diagonal, you have the remainder, then you can find your inverse diagonal, right? Then you can find your inverse diagonal multiplied with B, which is 11, 13. You have this. Then also you have this inverse diagonal multiplied with R is this, right? So then you can do step by step lah. So assuming iteration by iteration, assuming the 0 iteration, at the initial value I put 1, 1. Okay, so if you still remember our x k plus k plus 1, or the next iteration equals to d inverse b. Okay, right, d inverse b, okay, minus d inverse rx, right, minus d inverse our r, then we have the x of k, the previous iterations. So in this case, if I have my negative, this is this one, okay, so I will put at the front, multiplied with my current value. You will see this my current value or current x value. Then I will get my next iteration value, which is 5. This is my x 1. So this value will be substituted into here for the second iteration to find my x2. Okay, so you can see that after 22 iteration, probably you have seen that the 21 and 22, the difference between the x21 and x is very close. 22 is very close. Okay, of course you have to set a stopping criteria, the tolerance. They are very close, then it stops. Then it will give you the solution of x1 equals to 7.111, x2 equals to negative 3.222. All right, so that is Jacobi method in terms of matrix form. Gauss-Seidel methods, again, similar, very similar, just that now, if you look into this mathematical formulation, so you see that x1 k, to calculate x1, it used your initial value x k minus 1. Okay, so you have x I k minus 1 all value, because you don't have any value of x yet in this case. Okay, so you use all the initial value to calculate x1 for the first iterations, right? Then you have the x1 to calculate x2. Okay, to calculate x2 k of that second iteration, you also have you already calculated the x1. Okay, x1 of the iterations, so you use back this x1 to here. Then the rest x2 x3, x4 until xn, you do not have the value, the updated value of the iteration, then you use back the k minus 1 value to calculate your x2. So now you have, after the second equation, you have an x2 of the k iterations. To calculate x3, k, now I can use my x1, x2, k iterations plus x4, x5 until xn, my previous iteration, k minus 1, because it haven't calculated yet. So what it means here is Gauss-Seidel basically, it consider all the current values, okay, of your x, okay, that have been calculated for the iteration it used. Okay, so for example here, if you want to find your xk of any numbers, 1, 2, 3, 4, 5, x1 until xn, then whichever value that have been computed of that particular iteration, it will be using. Okay, the rest it will follow what the Jacobi method use. Okay, using the old or initial values from the very beginning of the previous iterations. Okay, so that is what it means. So in terms of matrix forms, okay, also the same lah. It will also you can also decompose into D, L, and U. Okay, so what it means here, you will see that we need the calculated one, right, of the iteration. So in this case, in terms of your diagonal matrix, okay, you also remain the what we call the lower triangular matrix at left hand side. Then you only move the what we call the upper triangular matrix out to the right hand side. So after you rearrange everything, then you will find out that your xk, which is if you want to find any value of your x of the current iterations, then probably you have to find the inverse of d minus l. Okay, d minus l. Then you have your multiply with your u inverse, whatever u, whatever the xk minus 1, then your d minus l. So this d minus l here is basically your diagonal minus your lower matrix. So in this case, yeah, I mean, you have your this part, okay, plus this part okay, together. So that it will basically is some sort of our lower triangular matrix. Just that yeah, you have the we put it at the star here okay? So it's also part of our lower triangular matrix. So in the case of matrix form, if you want to solve it, right? So we need to find this L star. So this L star is basically our diagonal matrix minus our lower triangular matrix. So here, our L star here, the internal matrix is 16, negative 11, then we put negative at here, minus 7, then 0. Our upper, of course, is from the top here is 0, 0, 0, 3. Okay, so substitute into these matrix equations, okay, or this, then you can find our here we have this L inverse B, which is this part, and L minus L inverse U, which is this part. So again, putting into the equations in the matrix form, we start with the initial value. Always we have an initial value, okay, 1, 1 at here coming in. So you calculate here is your second iteration, substitute into here. Calculate your third iteration, substitute into here. So third x3 or your x over the third iteration you have calculated here, then you substitute to the form, in this case the matrix forms. Okay, it had considered the way the matrix is transformed, it is decomposed, is already considered this part what we have mentioned, these parts. Okay, the x, whatever the x that have been calculated, okay, or the x have been calculated will be updated using the updated value instead of the previous iteration value. The updated value at that current iterations, okay, instead of the previous iteration values. Okay, so that is how you do matrix. So for example, in this case, if you're looking into the difference between the two, if I have this Jacobi method, using Jacobi method, iterative method to solve this particular linear equations, okay, assuming our initial value is 0, 0, 0, okay, so what Jacobi method use is we rearrange this, you rearrange this value, okay, x1 equals to x1, x2, x3. So for x1, I need x2 and x3. For x2, I need x1 and x3. x3, I need x1 and x2. So the initial value x1, x2, x3 is important. No? So you substitute your whatever value that needed for x1, x2, x3 into the equations. So you will get your first iteration x1, x2, x3, which is 0.2, 0.222, and negative 0.429. Okay, so this value for the first iteration will be used again, substitute into these equations, okay, to get your second iteration x1, x2, x3. So you will find out that after 7 iterations, probably these values are quite close, doesn't change much already, then you stop. Okay, stopping criteria. Unlike Jacobi method, the Gauss-Seidel method, the same problem. Okay, so what it does is, okay, you start with 0, 0, 0, right? So substitute your x1. For x1, you need x2 and x3, right? So you substitute 0, 0 into it. So you get your x1 is negative 0.2 for the first iterations. So for your x2 itself, you need x1 and x3. So x1, because you have at the current iteration, you have already 0.2, negative 0.2, so you use it. Okay, but x3, you don't have any value yet, not updated yet. So you use x3 equal to 0. Okay, yeah. So calculate your x2 for the current iteration. 0.156, which is your x2, okay? To calculate x3, next is x3, right? So calculate x3, you need x1 and x2, which is 0.2 and 0.156. Negative 0.2 and 0.156. Substitute into here for your x3 to calculate your x1, x2, x3 of the first iterations. You know, that is the only difference between Jacobi and Gauss-Seidel, right? So for Gauss-Seidel, probably you only need here you need 5 iteration to solve or to stop basically to get a consistent result. Okay, in this case. So you can see that the first iteration's value is when you start in the first 0 iteration, all are same. Okay, even Jacobi. But then when you are doing the first iteration, the only same value is your x1 okay? Then your x2, x3 is already different. See, not the x2, x3 will be different between Jacobi and Gauss-Seidel because it already used it already. It used the x1, the updated one, to calculate your x2. Okay? Then x3, you use the x1, x2 to calculate. So will be different results. So we will say that it will be faster to converge. Okay, so convergence. Iterative, then you need to set a stopping criteria for it to converge or to stops. All right. So of course you are using what we call iterative method, right? So this so-called your A matrix. This is your A matrix. This is your A matrix. So your A matrix here is 5, negative 3, 2, negative 2, 9, negative 1, 3, 1, negative 7. Okay, so you need to follow a little bit of so-called rules. Okay, here is it have to be what we call strictly diagonally dominance matrix. So this A matrix have to be a dominance. Okay, the diagonal values it have to be a dominance. Okay, So if the absolute value of each entry of the main diagonal is greater than the sum of the absolute value of the others entry in the same rows. So what it means here, your A11, A22 until A33, ANN, okay, of that absolute values. So in this case is this value, okay, have to be greater, okay. Your 5 absolute have to be greater than here 2, 3, okay, greater than 2, greater than 3, right? So your 5 greater than 2, greater than 3. So your 9 greater than 3, 9 greater than your 7 greater than 2, 7 greater than 1, right? So that is what we call a strictly diagonally dominant matrix. Okay, so if A is strictly diagonal dominant matrix, then this linear equation given, so you have a solution, you have a unique solution. Either you use Jacobi or Gauss-Seidel method, basically you will get the convergence. Else, it will not converge, it will diverge. Okay, so for example, this case, if you look at this case, okay, when we talk about a strictly diagonal dominant matrix, so here our A itself is the 2 by 2 matrix is 1, -5, 7, -1. So 1, okay, your diagonal matrix is here. Absolute value, 1 is less than 5, 1 is less than 7, right? So compare this row by row, row by row. So here it is not a strictly diagonal dominant matrix. So if you solve this using Jacobi or Gauss-Seidel methods, then probably you won't get a convergence. So you will see it diverge. Okay, then you won't have a solution over the iterations. But if you rearrange it, okay, so in this case, if I rearrange again the what we call the equations, I will swap this to here, this coming down to here. Then I have my A now is 7, -1, 1, -5. Then here I have my 7 larger than 1, 5 larger than 1. So it's a strictly diagonally dominant matrix. So after 5 iterations, okay, it have been converged. So if you can see my screen, okay, so if you see a format, that is the coding between Jacobi and Gauss-Seidel, if you see that. Okay, so Jacobi, if you see from here, I have a stopping criteria, the error, okay, it have to be 0.001, the difference, so it stop. And you will see that the x itself, it use always the previous, right? The previous so-called x, the previous iteration x. Unlike these Gauss-Seidels, okay, so everything the same, the only difference is it use any x that available, right? If you have the available x that have been computed, then x1, x2, x3, right? So you are in the x4 calculation, so x1, x2, x3 available, then it will use this x temporary, okay? So that's the only difference. So in the case of I have a matrix, let me show you. So if I have a matrix of like what you see just now, 5, 2, 5 just now is what value? Just now you have this 5, -2, 3, -3, probably at here, here, right? All right. So Jacobi method, if you have this, right? So if we undergo, we complete this particular matrix using solutions, we solve this particular matrix, the problems, okay, or equations using Jacobi iterative methods, then you will see that after 7 iterations, right? So it stopped converge. Then this is my A matrix. This part is my A matrix. Okay, this is my X matrix. This is my B matrix. So end up I have 0.1861, 0.3313, -0.4226. So this is my solutions of X. Okay, after 7 iterations. Right. So for Gauss-Seidel also the same lah. I mean, if you look into this. So the same one coming in. So five iterations. Okay, you have solved the x lah, x1, x2, x3. So this is my x1, x2, x3, or this one is my x1, x2, x3 in the 5th iterations. All right. So that will be. So again, if you are having the not strictly diagonally dominance matrix, like you have seen here. Okay, so let me show you. Or Jacobi also the same. So if you have this particular problem that we have seen just now at here, not strictly dominance. Okay, so you have a 1, -5, 7, -1. Then my B is -4 and 6. Right. So if I solve it, then you see that it will go infinities, right? It won't actually converge. At the end, you won't have a solutions in this case. Okay, it's infinities. So if we just change a little bit to the other way around, then you will solve it in four iterations, right? So you will end up that is 1, 1. Your solution x1 and x2 is 1. All right, so that is what you have seen. So that ends basically wrap up everything. So, I mean, if you still remember from we have direct methods and also iterative method. So iterative method, of course, you can solve it using Jacobi or Gauss-Seidel, but you have to make sure that your A matrix is strictly diagonally dominant matrix. Then for direct method, you of course can use the Gauss elimination methods that we have learned since our secondary. Then of course we also can use the LU decomposition method, lower triangular and upper triangular decomposition methods, which involve it involve a little bit of computations to build the L matrix and U matrix. You can use it, or the easiest way, if you have access to tools like Excel, like MATLAB, then will be even easier. I mean to use to solve it. So for example, probably I can, if you have access to MATLABs, okay, then probably I can build a matrix of this, right? A equals to 2, 1, 1, 3, 2, 4, 5, -1, 3, which is I think is our previous examples, that under Gauss elimination methods or the LU methods. So this one, 2, 1, 1, 3, 2, 4, 5, -1, 3, right? So I can build 2, 1, 1, semicolon, 3, 2, 4, semicolon, 5, -1, 3. It will build this A. Then I have my B, or my is 13, 32, 17. So I can also build this B, okay, here. Okay, maybe I clear off this. Okay, so I rebuild again my A matrix. Okay, it's already coming here. So if you look into it, okay, you have the A also at here matrix. Then I can build my B matrix. Okay, now I want to find my X, right? So what I do is, you still remember our X is equals to A inverse multiplied with B, right? So what you can do is, of course, we can do something like a code like this: X equal to inverse A multiplied with B matrix. So if you do this, then you get your x1, x2, x3, 2, 5, and 4, right? Or another way is using this backslash. Right? So x equals to inverse A multiplied with B. Basically, it's A backslash B. Okay, you also get the x1, x2, x3 equals to 2, 5, and 4. All right, so that is another way. If you have, of course, we can use matrix methods. Okay, inverse matrix method, you can determine using your inverse matrix methods, finding the determinant, finding the adjoint to find it, okay, manually, no problem. So we have three methods. I would say that direct method, we have three methods. Either you use matrix, inverse matrix method, Gauss elimination, or LU methods, right? But then if you have access to tools, computation tools like this, then software like this, then probably you can use the codes to solve it. Okay, or if you have Excel, right? If you have Microsoft Excel, then also the same things. Okay, I can show you another way of solving. If you don't have MATLAB, because MATLAB probably you need license, right? So if you have this, we can use Excel. Excel can do matrix solution also. So what you need to do is just build the matrix out. So I have my A, okay, matrix. Okay, I put my A matrix. So I might have my A matrix is 2, 1, 1 in each column and row. 3, 2, 4, 5, -1, 3. Right. So what I need to do is just I need to group them and define them as a matrix A. So what I do is I select them. Okay. Then at here I put mat A. So what I do is you click, you press Shift Control together, then followed by Enter. Okay, so if you do this, Shift Control and Enter, so you can find your matrix A is selected. From here, there is a list already. So if I just now I rename it as mat A, right, underscore A. So I click on this, that is my matrix. Okay, so later on we can use. So this is what I previously defined. So just this one is the just now that I have defined. So this is my first matrix. Shift, Control together, then followed by Enter. After you have select and rename it. Okay, so then we have our B matrix, right? Our B matrix is equal to what? 13, 32, 17. 13, 32, 17. Right? So this itself, we have to select it. Then this, we put it at a mat B. Okay? Then you put Shift, you press Shift, Control, and Enter together. So again, you have your matrix defined. Right? So I need to find my x, right? My x is to find inverse of A multiplied with B. So first we have to find the inverse of A, right? So here I put inverse A, okay? Then I can probably use equal, the functions are M matrix inverse. M inverse, yeah, M inverse, okay? Then you have to find your array. So here we have our mat A that we have determined, right? The whole matrix, the inverse of this matrix A. So you close the bracket, enter. So it will give me the inverse of this 3 times 3 matrix, right? Then I need to find my x. Okay, my x is inverse of my A, inverse of my A multiplied with my B. So it's multiplication, matrix multiplication. So equals to M multiplied, which is this one. Okay, the functions. So you need two array, two matrix. So it's inverse of A, 3 times 3 matrix, which is you find inverse. Yeah, we have to first we have to rename what we call name it, group it first. So this is my inverse, right? So again, I put IMV IMV mat, okay, A, right? So Shift Control Enter. So I should have this. Okay, I should have my A. I should have my B. I should have my inverse matrix AB. Okay, right? Inverse matrix A. This one. So to find my X is equals to multiplications of matrix. Then first I have to find my inverse matrix A, which is this one. Then another one is my matrix B, which is this one, right? Then we close bracket. Then it will give me 2, 5, and 4, which is my x1, x2, x3. Right? So that is, yeah, another methods. If you have Excel, then probably it can help you to solve the matrix. Why we are doing this? All because we are solving a set of linear algebraic equations from what we have formulated from using the FEM methods. FEA methods. All right.